test.
Huh?
I know you can't see the numbers, but number 5, for example, it's a show organized steps in an F double prime number line to answer the same 3 questions for these functions.
Where it's increasing, where it's decreasing, and whether there's a min-max? Or different questions?
The intervals where the function is concave upward, concave down, and points of inflection.
Okay. And what's the function?
F of x equals x to the 4th minus 4x cubed plus 2.
What's the first derivative of it?
4x cubed minus 12x squared.
And what's the second derivative of it?
12x squared minus 24x.
Okay. So it's the function itself is going to be concave up whenever the second derivative is positive. And that's the way I like to memorize it, because up goes with positive. And it's concave down whenever the second derivative is negative.
Okay.
Okay. So the first 2 questions get answered by setting this thing greater than 0, which gives us what solution? Let's see, that gives us 12x times x minus 2 has to be greater than 0. So that occurs where? That occurs there, and let's see, key points are 0 and 2. If x is negative, it's a negative times a negative, so it's positive there. When x is 1, it's negative, and it's positive there.
Are you plugging that into the second derivative to find that?
Yeah, all I'm doing is trying to solve that inequality right there.
Okay. Yeah, I think I got confused. When she tries to find points, she plugs it into the first derivative or the original.
Well, let's go through it, because I think I understand where your confusion is coming from. But in terms of determining whether concave up or concave down, the original function, we need to solve the second derivative where it's greater than 0. And that's all I've done. In other words, what this picture says is that the second derivative is positive whenever x is less than 0 or whenever x is greater than 2. And it's where the second derivative is positive that it's concave up. Let's graph this function, and I can explain it probably a little easier. Graph it with Wolfram alpha, which, if you're not familiar with it, is a wonderful online tool. I think I told you a little bit about it. X to the 4th minus, I do need my keyboard for this, x raised to the 4th minus, what's this, 4x raised to the 3rd minus 2?
Plus 2.
For this problem, I don't think that's going to matter, actually. Since the second derivative, that goes away anyway. So, let's see. We can see that they always give you two scales when they graph this. And in fact, let's just look at this for a second, because if you're not familiar with it, this is really worth checking out, everything that they give you. They give you this scale, which you can see, shows it up close. They give you this scale, which the y is expanded by like a factor of 1,000, and the x by a factor of 10. So that you can't see much in detail on that. They give you the real roots of the function. In other words, the zeros. Always. Whenever you want to find the zeros, they'll automatically give it to you. And, of course, the complex roots in the complex plane they give you. A lot of stuff they give you here I'm not even sure I understand. They give you the first derivative. They give you the integral. They give you global minimums. Lots of cool stuff. But let's go back and look at the graph. My answer is that it's concave up when it's less than 0 or greater than 2. Well, greater than 2, we can see it is indeed concave up. It looks like it's concave down in this area right here. You see that?
Yes.
Okay. And then when we are less than 0 over here, it clearly turns concave up again. So what you can't see on this scale here is there's actually a place between 0 and 2 where it's concave down, but you can see it on this scale. With me?
Okay. Yeah.
Okay. So that tells us, that answers question 1, where it's concave up. Question 2 is where it's concave down. That's between 0 and 2. Question 3, where are the inflection points? The inflection points are wherever this second derivative is equal to 0. In other words, it's concave up where it's greater than 0, it's concave down where it's less than 0, and it's the inflection points come at the difference or the exact spot where the concavity switches from up to down. And those two spots are 0 and 2.
Mm-hmm.
Were those the only 3 questions you had to answer?
For those problems.
For that problem?
Yeah.
Okay, now I didn't get your email. Let me just spell out my email. Make sure you didn't leave off the 1949. Because let's get this down pat. Because once you successfully send one picture, then the next time you go to send one, is all you have to do is type in the first 2 letters, and it'll present you with my full email, which you can then just pick. Is that where you sent it to?
Yeah, I misspelled your last name.
Okay.
That's why.
Yeah, go ahead and change that, and let's go ahead and have you send those.
Okay.
Of course, now, the next time you bring it up, it's going to give you 2 options. My last name misspelled and my last name spelled correctly. So, do you know how to delete the one? I'm not sure I know how to delete one that I have in there. What kind of phone do you have? Is it an iPhone or a
Yeah, it's on an iPhone.
Android? I'm not sure how iPhones work. I'm not sure I would know how to delete a one that came up in mine. Maybe it won't remember it because that email probably is not going to go through. Although it might. There might be a David Cowan out there who has this email with it spelled W-E-N.
Alright, let's get this real quick.
And while you're doing that, I don't want to interrupt you, but remember when I said that you can't take negative numbers to fractional exponents?
Yeah.
This is a very interesting problem. What is the solution to that?
Is it?
First, take the cube root of 8 and then square it.
It's 4?
Uh-huh. Now, what is the answer to this? Hold on. There. Got to put it in parentheses.
Is it still 4?
Nope. It's 1 point something.
Oh.
And the explanation is not easy math. It's really high-level math. I had to do some tracking down on the internet to understand this. The explanation is actually you get a complex number when you take a negative number to a fractional exponent. And that's as much explanation. But the fact that the answer is not 4 is what's amazing, right? Because the cube root of negative 8 is negative 2. And then if you take negative 2 and square it, you would think it would be 4, but it is not. If you put that into Wolfram alpha, it'll give you a complex number and it won't be 4. Which had to do with one of the problems you had, which was something like x to the 2/3. Remember that problem?
Yeah.
And I had to take the derivative of it, and I was wondering, well, is the domain of this thing? It is. All positive numbers or 0. The domain does not allow for a negative x. Okay, there's your email. Let's bring it up here. Here we can see it. Okay. I've had this problem with other Apple iPhone users. When you send the photograph, you have to specify high res. And I think there's 2 choices. There's a low res and a high res option.
Okay.
Can you try it one more time? I hate to waste this amount of time, but it's worth getting right for the future. I don't know that it has to do with when you actually take the picture as much as when you send the picture. I've tried to understand, but without an iPhone, it's a little hard for me.
I'm not really even sure where that option's at.
Yeah, I'm not either. I'd have to ask one of my almost all my students have iPhones, and I had one of them explain to me what happened, because they had the same problem. They sent a picture and it came out blurry. And then they went back and they resent it. You might, maybe it is an option when you take the picture. I know on my phone, the camera, there certainly is an option for high res when I take pictures. But if I remember right, the student told me that it's when you send it or attach it as a file that you have to express high res.
Okay.
And if you do, it comes out crystal clear. I mean, Apple, the files I get from Apple iPhones are far clearer than any other camera. You'll see how nice and clear it becomes. I mean,
So once I attach the file?
I don't know where the option is. In other words, I don't know how to do it myself. I just know that it has to be specified that way. Let me see. Let's see. I looked at this one. No, I can tell. because it came in tiny, I can tell that this isn't the right way. In other words, when I blow that up, it's going to be blurry.
Oh, so if I use a bigger size for it?
Yeah, that's it. That's the way to do it.
All right.
When you said those words, I now remember that that's what the student had to do. So
Okay.
I'm going to put those in the bin. Now I'm curious, when you go to send that and you type DA, do both of those emails come up on your default list, or just the one with my name spelled correctly?
Both of them showed up.
Okay. Which is going to be problematic if you don't remember. In other words, so if you can figure out a way to delete the one that's spelled W-E-N, or however you spelled my name, that'll be helpful for you in the future. Let's see if this does the trick here. Yep. Let me get the other one. So that's the secret. You just have to send the size of the file is what matters. Huh? Okay.
All right.
Which problem are we looking at or want to look at? Okay, I see here. Here's the, and that's the first one we did was 5. Okay. Oh, and this one says use the appearance of the graph to answer these 3 questions.
Yeah.
Oh, I see. No, that's 1 through 4. And then 5 through 7 are use the second derivative.
Mm-hmm.
And notice she says the second derivative number line. No, that's what I put up there. Oops. That's what this is down here.
Yeah.
That's the second derivative number line. All right. You want to go over and look at 1 through 4, or do you need to? Are you good with those?
We can do one of those.
Okay, pick one that you're not positive about.
How about 2? Because the asymptotes.
Okay. Is 2 ever, well, it's actually pretty easy. It's concave down on what intervals?
Negative infinity to -2, and from 2 to infinity.
Yeah, with parentheses around everything. It's concave up on what interval?
From -2 to 2.
Correct. There's no real inflection point, but the I wonder what would happen if you had that function and you took the second derivative. The second derivative is probably not going to be defined. Yeah, well, even the first derivative isn't going to be defined here because you can't take the derivative. Even the function isn't defined there. So, okay, 3 is actually a little more complicated, or 4. 3 is concave up from there to that inflection point. Concave down from there to that inflection point. Concave up from there to that inflection point. Concave down the rest of the way. If you understand that, then you understand concavity.
Yeah.
Okay. Now, let's look at 6, on how to do 6. I assume that that's what you'd like to do, or?
Yeah, that's fine.
Okay. 7 is going to be the difficult one. That's got the 2/3 in it. In fact, is this the one we did? when I saw you? That looks familiar.
We did.
Yeah.
Let me find it here. We did x plus 1 to the 2/3.
Oh, yes, that's right. Because those were three different questions. That was where is it increasing, where is it decreasing, and where's a minimum and maximum. Okay, so let's see. For number 6, the original function is that. So give me the first and second derivatives.
All right, first derivative is 15x to the 4th minus 20x cubed.
And the second derivative?
60x cubed minus 60x squared.
Let's factor that.
You can take out 60x, x squared. Is it 60x to x squared minus 1? Yeah.
See, did I do it right? Yeah. You can see my screen here, correct?
Yeah. Would it be 1 in the parentheses or just, oh, you took out x squared? Never mind.
Yeah, I factored out the greatest common factor.
That's where I messed up. All right.
Okay. And so now the three questions is where is it concave up? Where is it concave down? And where are the inflection points? Okay, so we're going to do a sine curve. What are the key critical points here?
0 and 1.
It's the only time I put 0 on my sine chart. I don't put it as a basis because it gets in the way if it's not one of the critical points. So to the left of 0, what is this second derivative?
Is it negative?
Because this is positive, and that's negative. And that's always the way I do it. In other words, we don't care what the amounts are. And you can pick any number you want. If you pick minus 1, the only thing that's important is this part positive, and is this part positive or negative? Okay, well, minus 1, that part's positive, that part's negative. So it's negative. And if it's negative at one point to the left of the critical point, it's negative everywhere to the left of that critical point. In between, what is it?
Is it negative as well?
And finally, when it's greater than 1, this part's positive, that part's always positive, so it's like that. Well, this answers an interesting question I had. I once had a student tell me that the teacher said these always alternated, and clearly they don't.
Yeah, my teacher calls it a 95% rule, or 95% of the time they will.
That answers a lot, because when that student told me that, it seemed like I had come across functions that didn't alternate, but I couldn't think of one. Okay. So it's greater than 0 when it's greater than 1. It's less than 0 when it's less than 1. And it's equal to 0 at both of these critical points. So I would expect inflection points. But there's a problem. How can there be an inflection point right there? Because we're going from concave down to concave down. So let me think about that for a second. The second derivative is equal to 0 at x equals 0. Let's put this thing on Wolfram alpha and take a look at it. And notice that when I'm looking at Wolfram alpha, I'm going to look at the original function. That's the one I want to see, because that's the one we're talking about. The beauty is it tells you if you put it in right. And I did. Okay. Again, on the detailed scale, you can certainly see that to the left of 0, it's concave down. From 0 to 1, it's concave up, concave down. There clearly is a inflection point at x equal 1. In other words, where it switches from concave down to concave up. So that inflection point makes sense. Why did it give us something at 0 that looked like it was an inflection point? It's actually the point where the first derivative is horizontal. So
Is that where there's no concavity?
no, not necessarily. In other words, if I had something that looked like this, at that point right there, the first derivative is horizontal, which means it's 0, and yet it's concave down throughout that interval, even though the first derivative is 0 at this point here. In other words, if I put an axis on there. Let me think. What this is telling us is that when you find the second derivative is equal to 0, it is not always an inflection point. Which I didn't know. Well, let's go beyond this issue. I'm a little confused about it. I mean, it makes sense that there would not be an inflection point there because you need the signs to change of the second derivative. Why the second derivative is equal to 0 at 0 puzzles me. The first derivative, incidentally, is also equal to 0 at x equals 0, and that's why we know that that's a horizontal tangent line, which is what the graph kind of shows. In other words, the full graph is this one down here, where you can see very little of this detail, but one thing you can kind of see is that it sure looks horizontal at 0. It definitely is horizontal at 0. But that's not an inflection point. Not the way I understand it. And how we know that without graphing it, I guess you can say that you can figure it out algebraically because an inflection point has to be where the concavity changes, and it doesn't change there. You can see by the line chart that the concavity doesn't change, and so that in itself rules out, well, I didn't mean to mark that out. That rules out the 0 answer for this solution. Yeah, I think that's satisfactory enough. So we have a word of warning that just because the second derivative is 0 doesn't mean it's a inflection point. All right. Let's look at this other one here. Let's see. Before we do anything, let's graph that. X to the 2/3 what is it, minus 3?
Yep.
We put it in there properly. Interesting. There's a complex and a real part everywhere in that domain. And the only reason we're seeing values to the left of the y-axis here is because it is plotting the real and the imaginary part.
Okay. Okay, yeah.
All right, so let's go back and take our derivatives. What's the first and second derivative here?
First derivative is 2/3 x to the negative 1/3.
And second derivative
is
always start by taking your exponent, that's your starting spot, multiplying it by the coefficient.
Yeah. So negative 2/9. So negative 4/3. Yeah.
So the question becomes, where is that greater than 0? Where is it less than 0? And is it equal to 0? Ever. Well, let's see. Only critical point should be 0. Right? In other words, it's whatever makes the numerator or the denominator 0. And I can rewrite this. Let's rewrite it. Minus 2 over 9x to the 4/3. I can even put that minus sign out here. Well, clearly when x is positive, this is negative. Right? In other words, when x is positive, the denominator is always going to be positive.
Okay.
Okay. When x is negative, and this again, as we get back into the question, is can x even be negative? Well, gosh, when x is negative, you're going to have a cube root of it, which will be negative, taken to the 4th power, where you would think it would become positive. According to this picture, when x is negative, it actually looks like it's concave up, which would mean it's positive. We can see clearly that when x is positive, it's concave down, which is what we came up with.
Mm-hmm.
And if and indeed is concave up to the left of 0, well, then the inflection point is at 0, and that's where the second derivative is equal to 0, is at 0. So I guess I would have to say it's concave up to the right of 0, concave down to the, excuse me, I got that backwards. It's positive this way. It's concave up to the left of 0, concave down to the right of 0, and the inflection point is at x equals
0. All right.
Yeah. And notice the second derivative is not defined at x equals 0, but the function is. That's why we see it here. But if I were plotting either the first or the second derivative, I would have a vertical asymptote at x equals 0.
Okay.
But I don't think that matters. Yeah.
So I just had a quick question.
Yeah.
Define the exact point where the inflection point is. Would you plug that x value you got from the second derivative into the first derivative?
You don't need to.
Okay.
Well, you have an inflection point wherever the second derivative is equal to 0 or not defined.
Okay.
And in this problem, the second derivative is not defined at x equals 0. But it's still x equals 0 that represents the inflection point on the original function, at least according to this picture.
Okay.
In other words, that's the thing, and that clearly not concave down, that's concave up from this angle or that. And the function is defined at x equals 0, so it's x equals 0, and when you say plug it in, we don't need to plug it in to any of them. In other words, once we come up with the inflection point, once we solve the second derivative function for where it's equal to 0 or undefined, then we have our answer.
Okay.
I know where you're getting confused, but I need a different problem to straighten you out. It's not this one.
Yeah.
And the problem is which thing do you plug it back into? Well, to determine whether it's greater than 0, you're plugging it into that.
Mm-hmm.
I plugged any positive number. I tried 1, and when I tried 1, I got a negative answer. Therefore, the second derivative is negative at x equal 1. That means the original function is concave down at x equal 1.
Okay.
Okay? Maybe we'll come up against a problem that will require us to plug it into the first function, and I can straighten you out, I think. I got to see the problem, though, before I can think about solving that problem. Use the second derivative test to find the relative extrema points. Okay. Let's do 8. That's the easiest one to take the second derivative of. Let's see, if I take the first derivative, I get 3x squared minus 6x. We did this one, didn't we, or not? Is this one you verbalized? Yeah. Because then we factored it out, and we had 6 times x minus 1. That's our second derivative. And if we're looking for extreme points, why are we using the second derivative to find relative extrema? It's one way to tell whether the extrema are minimums or maximums, but in terms of finding the point where it's extreme, is example 7 on one of the sheets you sent me here?
No, that's on one of the note sheets. I can send it.
Well, I'm curious on what she's doing in example 7. How is she using the second derivative test to find the relative extrema? If you want to send it, you can. If it doesn't take you too long to do it, go ahead.
Okay, yeah. I'm going to do it real quick.
Okay. In other words, the way I would do this problem is I would take the first derivative to find where the extrema are, and then I would take the second derivative to find out whether it's positive or negative at those points.
Yeah, that's what she did.
Well, I'm going to plug those. Okay, so I don't need you to send it then.
Yeah.
Let's do it that way. Okay, so the first derivative is the top line, and I want to find out where that's equal to 0 or undefined. Okay, let me even erase this. Well, again, I got to factor my greatest common factor out. That's that. So I want to know where that's equal to 0. What two places is that equal to 0?
0 and 2.
Okay. Now we're going to use the second derivative to figure out what kind of an extrema it is. Second derivative is 6 times x minus 1. Right? Let's see, it's 6x minus 6. Yeah. Okay. So if I plug in 0 into the second derivative, I get negative. That means, negative means concave down. That's a maximum. If I plug in 2 into the second derivative, I get positive. That means concave up. That means minimum. So I found the two extreme points using the first derivative, but I determined whether they were minimums or maximums using the second derivative. There's also a first derivative test that I could have done. I didn't have to take the second derivative to determine maximums and minimums. I could have looked at the first derivative line chart. Just like you told me how your teacher did it, when you go from plus to minus, that's a maximum. When you go from minus to plus, that's a minimum.
Okay.
Okay? But she wanted you to be forced to use the second derivative test to determine whether it was maximum or minimum at those 2 points. And we're going to use 9, we're going to do 9 exactly the same way. We're just going to take the first derivative and solve for where it's equal to 0. It's not going to be undefined anywhere. So it's just where that's equal to 0. You'll come up with 3 points perhaps, because after we take this derivative, we're going to have a cubic. So a cubic usually has 3 zeros. So you'll find 3 extrema on number 9. And I certainly can go through number 9 with you, but with only 10 minutes to go, you may choose a different problem if you want. In other words, after we take the first derivative here, we're going to have a cubic. We're going to solve that cubic. We're going to have 3 solutions. And then we're going to plug in all 3 of the solutions into the second derivative, merely to determine whether they're plus or minus. And it's occasional where the second derivative will be equal to 0, and you'll have to actually resort to the first derivative test. And so it might be worth doing the math here just in case we have that situation here. In other words, the second derivative test isn't always, it's only like 95% of the time conclusive. If it comes out to be 0, you don't know what you have. You don't know whether it's a minimum or a maximum. You go back and you do your first derivative test to tell.
Okay.
So there's another case where with the second derivatives equal to 0, it's not necessarily an inflection point. It can be the tangent line, flat tangent line. Okay, so what do you want to do next? You want to solve 9 completely, or do you want to do one of these others?
We can go through 9.
Okay, let's do it. First derivative.
Negative x cubed plus, let's see,
Well, they make it a little easier with their numbers.
plus 9x.
Okay. And where is that equal to 0? Factor it.
It'd just be, hold on. So at 0,
Well, let's factor it first. So I'd factor a minus x out, leaving behind x squared minus 9. So solve that.
okay, x, so, which would then be,
And that factors more. We have difference of perfect squares there. So
yeah,
it's another reason why you want to factor out a minus x.
x equals 0, negative 3 and 3.
Okay. Now, what's the second derivative?
Let's see, negative 3x squared plus 9.
Okay. So now we want to take those 3 points we came up with, 0, minus 3, and 3, and plug it into the second derivative and see if it answers any questions. Well, when we plug in 0, it's positive, right?
Yeah.
So this point, positive means concave up means a minimum. When we plug in minus 3,
It's negative.
it's negative. It's concave down, that means a maximum. And we plug in plus 3, it's negative. So that's also a maximum. And that's certainly possible that we have 3 different types of concavity there.
And 2 relative max is okay.
In other words, well, if I wanted to graph what this function might look like, I know I have a maximum there, I know I have a maximum there, and I know I have a minimum there. Okay, so what might that look like? Something.
Okay.
And they didn't ask for inflection points, but inflection points are going to be right there and somewhere right there probably. And you can tell if we try to solve this that x equals square root of 3 plus or minus square root of 3 is going to be the 2 inflection points. In other words, if I solve the second derivative for where it's equal to 0, you get plus or minus square root of 3. Okay. What are they looking for on 10? Oh, for these problems, find the x values of the relative minimums and the x values of the relative maximums. Well, let's see. Second derivative is negative. That means concave down. That means maximum. So at minus 3, that's going to be a maximum. At 3 is going to be a minimum because the second derivative is positive. And at 1, second derivative is equal to 0. So we don't know what that is.
Okay.
So I'm not sure what they want you to say. They don't give us the function, so we can't even look at it to figure out what's going on at 1. Looks like it's probably the inflection point. Since we're going from concave down to concave up, there must be some point between -3 and 3 that's an inflection point, and that looks like a pretty good candidate.
Okay.
Now what are they doing on 11? F prime equals, so the first derivative evaluated at -2, 0, and 4 is equal to 0, so your critical points are -2, 0, and 4. And the second derivative, plus minus chart, tells you that -1 is the inflection point between concave up, this minimum, concave down, this maximum, and concave up, this other minimum. So we have 3 points that are going to have a horizontal tangent, kind of like this thing I drew over here. Notice there's 3 points where the first derivative is equal to 0. Well, there's 3 points where the first derivative is equal to 0 here. In fact, this chart almost duplicates what the original function could easily look like, what I've drawn over here, only it's not at -3, 0, and 3, it's at -2, 0, and 4. That it might look exactly like what I drew over there. All right. Let's see how much time. We don't have much time left. Let me just take a look at, that's one we just did. And I don't have time for a long one, but do you have any questions or anything?
Let's see.
Like 17, maybe?
Ooh, yeah.
Okay, the mean value theorem basically says the following. I've got my theorems right. And that is that if I have a function like that, and I can figure out the average rate of change between any 2 points, which is the slope of that line, then there has to be some point where the slope is parallel to that. In other words, you can't get from here to here on a continuous function without having the slope of the tangent line be the same as the slope if this point is A and this point is B, then the slope would be f of B minus f of A all over B minus A. That's the slope of the straight line. Is all the mean value theorem says is that at some point between A and B, there's going to be another place where the slope is equal to that slope. Has to be. You can't get from there to there without, kind of like you can't go from 10 miles an hour to 90 miles an hour in your car without going through 60 miles an hour. You can't skip over 60 miles an hour.
Mm-hmm.
It's kind of another example of the mean value theorem. So just quickly, what I would do on 17 is find out what the average rate of change is on that interval by doing f of 6 minus f of 2, all divided by 6 minus 2. Okay, that gives you the average rate of change. Take the first derivative of this function and set it equal to that average rate of change, and you will solve for the C value that has to be there. In other words, in my example, this would be the C value. I knew that there had to be some C on that interval that equaled this.
Okay.
So that's what you're going to do on that problem. And in fact, what's the average rate of change? You got 2 minus 0 all over 4. So the average rate of change is 1/2. In fact, we can do this really quick if you want.
Mm-hmm.
Did you see how I got the average rate of change?
Yeah, the function of 6 minus function of 2 over 6.
Evaluated at 6 minus the function evaluated at 2, all divided by 6 minus 2.
Yeah.
So that gives you the average rate of change, which is 1/2. So if I take my first derivative, that's equal to 1/2 times x minus 2 to the negative 1/2. So I'm looking for where the first derivative is equal to 1/2. So I'm going to solve this problem. There's the first derivative. I know that over that interval, average rate of change was 1/2. There has to be an x to solve this problem. Well, that's equal to 1. Oops, excuse me. So now I get 1 equals x minus 2 to the 1/2. X has to be 3. So, or C has to be 3, excuse me. Because you're looking for a point in that interval where the first derivative, in other words, if I plug in x for 3 into the first derivative, I get a slope of 1/2. And that's what I'm looking for. Those can be a little tricky to understand. It took me a long time. I could figure that's just a little tricky, but not that tricky.
Mm-hmm.
All right, probably a good place to stop. Okay, let's look at my calendar. Jackson, do you want to take this spot every Friday at noon?
Yeah, that'll work.
Okay. I'll lock it in for you, and next Friday is all I will do is text your phone the meeting ID number. I won't call you first. Okay? And your GoToMeeting is all set up for the audio, so you won't have to do anything but put in the meeting ID number, and we'll be all set to go.
Okay, and it's installed on the computer, so I just have to go to that.
You should see an icon. If you make your desktop available, you should see an icon that looks like this orange flower here. You see anything that looks like that on your desktop?
Yeah.
That's the one you want to double click. And when you double click it, it will ask you for a meeting ID number, which I will have texted you.
Okay.
Okay? Now, the last thing is to see a copy of this